Welcome back. It's time to actually calculate some confidence intervals. Let's do this. So in this lesson, we're going to calculate a confidence interval. We're going to talk about the factors that influence a confidence interval, such as sample size, variance, and the level of desired confidence. And I'll briefly show you some confidence interval stuff in R. So let's get into it. Let us calculate. So confidence intervals. Before we even start calculating, actually, let's remind ourselves, why are we doing this? Why create a confidence interval? Because rarely is our 1-point estimate, the mean that you calculate, for example, exactly the parameter or the truth. So rarely does your x bar equal exactly mu. More than likely it's going to be a little bit off. Maybe it'll be a little too high or a little too low. So to increase our chances of capturing that true mu, we put a little wiggle room around our point estimate, a little bit of cushion, and we create this confidence interval. Then we can be, in this example, 95% confident that the true mean height of women is somewhere between 64.5 and 66.5 inches. You can also think of it as two different ways to fish for the truth. So if the truth tuna is somewhere out there swimming and we're trying to capture it, do you think you'd be more likely to capture it with just your one fishing rod that you cast and hope that whatever it is you catch is the truth? Or would you rather put out a net and increase your chances of capturing that truth tuna? Go with the net. The net is better. Now that I've hopefully won you over about confidence intervals, let's actually look at what goes into calculating one. So first we start with our x bar, that is the mean that you went out and calculated. Then we are both going to add and subtract, because we're going to get two different numbers, this whole thing here. This whole part of the equation is called the margin of error. It's basically that more or less más o menos cushion that you're going to put on both sides. You're going to add and subtract that value from both sides. So what goes into the margin of error? There are two main things. This one we're somewhat familiar with already. It's our standard error. We have our sigma divided by the square root of n. And here we have our z critical. Now, our z critical is basically the level of confidence that we want. So if we want 95% confidence, we would use the z value associated with that, which is 1.96. This is the same equation, but sometimes I like to write out the equations in words, just in case that's helpful to anybody. So you take your point estimate and you add and subtract all of this, your margin of error, which is made up of your z critical and your standard error. So let's see an example how using a net is more effective than using just one single fishing rod. Let's say I gave out a quiz to my stats literacy course. The standard deviation for the entire class was 8, and now we take a sample of n equals 9 from our statistical literacy population, and we calculate a mean of 81. Calculate a 95% confidence interval. So here is all of our information and the things that we need to solve for, such as the standard error, the margin of error, and of course our confidence interval. So what I'm asking you to do basically is, if 81 was the average you calculated, what is the highest possible value you think it could be and the lowest possible value, because we acknowledge that it's probably not 81 because we took a sample. So go and find the lower bound, or one side of your net, and the upper bound, the other side of your net. Now we can calculate our margin of error. Now, how did I get the z critical? Where did that come from? What is the z value associated with 95% confidence? 1.96. That's where that came from. So now you take the desired level of confidence, that z value, times your standard error, and you get 5.23. This is now our margin of error. This is that plus more or less you're going to put on both sides of your point estimate. So now all you have to do is add those to both sides. Now that we have our standard error and we know our z critical, because if we want to be 95% confident, we know that the z value associated with 95% confidence is 1.96. So 1.96 times our standard error, 2.67, and we end up with 5.23. And this is our margin of error. This is what you're going to add and subtract to the point estimate that you calculated, that average. So when we add and subtract 5.23, that margin of error from our point estimate, we end up with 75.77 up to 86.23. So the true population average for everybody in my stats class who took the quiz is somewhere between 75.77 and 86.23. And we are 95% confident in this. Now, what does that part mean again? That means that 5% of the time, this will be wrong. This could be one of those 1 in 20 situations where we actually miss the true mu. But we're okay with that. We've already acknowledged that there's a 5% chance we'll miss it, but we can still be 95% confident. So now let's pretend that I reveal that the truth is actually 85. So maybe you took a sample of those 9 people and they had a slightly lower average because of random chance. You just picked some people who got a slightly lower score on their quizzes. So let's pretend, again, that we know the sampling distribution, we know the truth. We can't and we don't, but let's just pretend for a second for the illustration. So here is our point estimate and our confidence interval around it. Now here's the truth. The truth is actually that 85, and we can put a little interval around that too. Now, did our confidence interval capture or catch in our net? Did we cast our net wide enough that we captured the truth tuna? Yes. You see how 85 is in that interval. It's close to the end of the interval, but it's definitely in it. So, we got it! Yay! We captured the truth, which is awesome. So how do we interpret this confidence interval? If we repeat the sample again and again, 95 times out of 100, the true mu will be captured in our confidence interval here. Again, just a reminder, this is completely theoretical. It doesn't exist in isolation. It depends on your sample and the sample size that you take, as well as the point estimate that you calculate. So you would never actually know this. But for the sake of learning, I hope that it helps you get this idea that confidence intervals give us a wider net to hopefully catch that truth. You find a research article that reports a 95% confidence interval for the number of hours college students sleep based on a sample of 9 students, that's very small, with a known sigma. They report a 95% confidence interval of 3.5 hours to 10.3 hours. That is pretty big, but that's okay. Let's just use it for the example. So first off, what is our z-value? We don't even have to calculate anything to know this. Because it's a 95% confidence interval and there is a known sigma, that means we're dealing with a z-value of 1.96. 1.96 if sigma is known and you are doing a 95% confidence interval, 1.96. So next, what is the point estimate? Now the point estimate can be determined by taking the lower bound and the upper bound, we add the two together and divide by 2. So it's basically giving us the number right in the middle, which in this example is 7. So the point estimate, the average that these people actually calculated was 7. So one way to visualize this is by thinking of that 3.5 lower bound, 10.5 upper bound, and somewhere right in the middle is our point estimate. And the distance from that point estimate to either the upper or lower bound is our margin of error. So let's go get our margin of error. There are 2 ways that you can figure out the margin of error. You can take the point estimate, so in this case 7, and subtract the lower bound, or you could take the upper bound and subtract the point estimate. Either one of these is going to give you the margin of error. You don't need to do both because they will give you the same answer. Now that we have our margin of error, we can also go and calculate standard error. Because we know that the margin of error is equal to that z critical times standard error, we can just rearrange it algebraically and take our margin of error and divide by the z, the critical z. And in that case, we get 1.79. That was our standard error. Now we have all of our information, and we see how the researchers got their confidence interval of 3.5 to 10.5. Awesome. But now how do we interpret this confidence interval? We could say, if we take repeated samples of n equals 9, and compute 95% confidence intervals each time, approximately 95% of those intervals would contain the true number of hours college students sleep. Another way we can say it is that we are 95% confident that the true number of hours college students sleep is between 3.5 and 10.5 hours. Factors that influence confidence intervals. So based on the equation above, think about what factors might influence how wide or how narrow your confidence interval will be. Think about it and hold on to those thoughts. So let's look at these 2 confidence intervals here. They both have the same point estimate of 15, but the one on top is a more narrow confidence interval than the one below it. What goes into widening or narrowing a confidence interval? The first thing you might notice is that the margin of error for the top one is smaller. It's only about 2 here, and over here it's 10. So margin of error seems to have quite an effect on your confidence interval, but remember, margin of error is made up of other things. So what affects your margin of error? So margin of error is affected by the sample size, the variability in the population, and the desired level of confidence. So now let's look at each one of these different factors. As sample size increases, what happens to your standard error, this whole guy right here? What happens to your confidence interval? Do you think it gets wider or more narrow? And what happens to your margin of error? So think about it. As your sample size increases, what is going to happen to these three things? So as sample size increases, the larger your sample size is, the smaller your standard error will be. Because remember, our standard deviation is going to be divided by the square root of n, and all of that makes up standard error. So the bigger this number gets, the more it can eat up some of that variance. Margin of error is also going to decrease as n increases because you're going to make your standard error smaller, and your margin of error is made up of standard error and your critical z-value. And it will also make your confidence interval more narrow because it makes your margin of error smaller. So all of these, the standard error, margin of error, and the width will all go down as your sample size goes up. Another way to say this is that there is an inverse relationship between sample size and standard error, margin of error, and the width of your confidence interval. Continuing on with sample size, are you more likely to miss that true mu that you're looking for with a small sample or with a large sample? You're more likely to be off if you have a smaller sample size. So to make sure that you catch the truth, you need to make your confidence interval wider. Here's an example where the point estimate is 66. But from a sample size of 36, our confidence interval would be somewhere between 65 and 67. Not too big. But if we only have a sample size of 4, our confidence interval gets much wider. It goes from that 65 to 67 now to 63 to 69. It has to get wider. We have to cast a wider net to try to capture that truth when we're dealing with such a small sample. So now let's shift our attention to variability. As population variability, or that standard deviation, increases, what happens to your standard error, your confidence interval, and your margin of error? As variability in the population increases, that sigma gets bigger, the standard error will increase because the bigger this gets, the bigger this whole standard error is going to get. The margin of error will increase because margin of error is made up of standard error and that level of confidence, so it will get bigger. And the confidence interval, because your margin of error is now bigger, will also get wider. As the amount of variability goes up, standard error goes up, margin of error goes up, and the width gets wider. So this is a direct relationship. There is a direct relationship between variability, standard error, margin of error, and the width of your confidence interval. And lastly, let's look at the level of confidence. If you increase your desired level of confidence from 95 to 99, what will happen to your standard error, the confidence interval's width, and the margin of error? Now here are the values associated with 90, 95, and 99% confidence. Thing to note here is that they are increasing. So 1.65 is for 90, all the way up to 2.58 for 99. So that number gets bigger. What happens if this number gets bigger? How will it affect everything else? So firstly, the standard error is not affected because standard error is made up of the variability divided by the square root of n. The level of confidence has nothing to do with that. So standard error stays exactly the same, is not affected at all by the level of confidence you select. But it does have an effect on the margin of error. The more confident that you want to be, the wider you have to cast that net. So your margin of error gets wider because margin of error is made up of the critical value, that level of confidence we want, times the standard error. And your confidence interval is going to widen because, again, if you want to capture that truth and be really confident that you captured it, you have to throw out a really, really wide net. And the wider the net, the wider your confidence interval. So in this case, the Z critical, or that level of confidence, has firstly no effect on standard error, but a direct relationship with margin of error and width. Now let's look at the relationship between precision and confidence a little bit more. The more confident you are, the less precise you're going to be, and the more precise you are, the less confident you can be in that precision. So let's look at this made-up example. I am 99% confident that the average age of this class is 19, or somewhere between 17 and 21. So look at that interval, 17 to 21, and I'm 99% confident in it. Now let's lower the confidence just a little bit. If I am now 95% confident that the average age of this class is 19 or somewhere between 17.5 and 20.5, notice how my confidence interval got a little bit more narrow. It's a little bit more precise, but my confidence has gone down from 99 to 95. Now lastly, let's look at this one. I am 80% confident that the average age of this class is 19 or somewhere between 18 and 20. So notice how much tighter my confidence interval has gotten, but my confidence in that interval has gone down. It's more precise, 18 to 20, more precise than from 17 to 21, but I'm not as confident in this as I am in this. Before we can move on to the wonders of inferential statistics and hypothesis testing, let's have a quick reality check though. If we are trying to calculate some estimates about something unknown, how likely is it that we will know a population's sigma, the true standard deviation? Not very likely. So unfortunately, we can't really use that normal z distribution anymore. But we do have another option. Up next, we get a bit more realistic and start using a different distribution where we do not need to know that sigma value. Next, we will start using the t-distribution. I will see you there. And now some confidence intervals in R. So here is the first example we did where we created the confidence interval around the average quiz grade. So first you would tell R the average quiz grade, the standard deviation, and the sample size. And now, because we're using the z-distribution, we know that a 95% confidence interval is associated with a z-value of 1.96, and you can also find the one for 99, which is 2.58. We assign those. Then we can get our margin of error by doing this calculation. So margin of error is equal to the critical value that we are interested in, times the standard deviation divided by the square root of n. So it's just a code translation of the equation that we already did by hand. Then you have your margin of error and you can subtract it and add it to the average that you initially put in here, and you can get your lower and upper bound.